So, hi dear students, today we are going to cover a topic called mutual inductance element. In this session, we are going to discuss mutually induced EMF in coils. So, here in this session, we are going to discuss on few topics, that is definition of mutually induced EMF. Then we are going to discuss a theory on the same. We are going to derive magnitude of EMF and expressions related to coefficients of mutually induced EMF. So let us not waste our time and just get start over it. Okay, so here as you can see, I have drawn one simple circuit. So in this circuit you can see there is one coil C1. In C1 you are having an alternating voltage source, and this source is having a current I1. So when I1 flows through circuit 1, it will create a magnetic field around this C1 coil, and since this magnetic field will interact with the another coil, that is C2, which is placed in a vicinity of that area, so that the coil will link with the magnetic field. Now once the C2 will link with the magnetic field of the C1, there will be an EMF which is induced across the terminal, and since this will be a closed circuit, current I2 will flow, right? So the phenomena of interlinking of magnetic field with these two coils is usually termed as mutual inductance. So as the name suggests, it is a mutual inductance, so you need two coils over this area, right? So let us go through the definitions. Mutual inductance, which can be defined as flux linkage of second coil per turn due to current flowing through the first coil. Okay, so this is what we derived from the circuit diagram which I have shown you over here, right? Now I will explain this process through some pointers so that you will get a deeper knowledge out of it. Okay, so here I have drawn one circuit diagram. Here you are having one switch. You are having a first circuit comprising of coil C1, variable resistance R, and C1 is having number of turns, that is N1, and another circuit which is comprising of N2 numbers of turn. Let us name it as C2, and you are having a current measuring or indicating source, that is galvanometer, right? Since this is a closed circuit, you will have a current, that is I2. Okay, so here you can see that two coils C1 and C2 are placed near each other. Coil C1 consists of N1 turns and coil C2 consists of N2 turns, whereas the galvanometer is connected in a series to the current in order to sense the current that is induced in the coil 2 circuit, right? As you know, the galvanometer function is to indicate the presence of current. Okay, now whenever the switch is closed, current I1 will start flowing to the circuit 1, and in the circuit 1 you are having coil C1. Now the current value or magnitude of the current can be changed by changing the value of resistance R, right? Now since the current I1 flowing through the coil C1, a flux is produced. Now let us draw some flux lines over here. See, this is a flux that is produced by C1. Let us term this flux as phi1. Okay, now since phi1 is produced, a part of this flux completes its path through coil C2, right? See, flux is not like a stationary member. Okay, this is all imaginary things. Your magnetic field will be up to infinite plane. Only thing is magnitude will reduce, right? So since these coils are placed in a vicinity to each other, the phi1 will complete path through a second magnetic circuit, okay, which can be denoted by phi2. Okay, now see this linking of phi2, which is produced due to the C1 only, but still it is getting interlinked with the coil C2. So this phi2 is nothing but a mutual flux, right? So this is what we are going to derive, what is mutual flux and how much magnitude of mutual flux we are going to get out of it. Okay, now if we change the current I1 through coil C1 by changing R, the phi1 will change, right? The flux will change, since the phi1 and I1 is directly proportional. So more the I1, the more your flux will be there, right? Now if phi1 will change, if I change the phi1, automatically phi2 will change, right? The mutual flux will be changing. Now according to the Faraday's law, there will be an induced EMF in the coil C2, right? Due to this EMF I2, it will be start flowing through coil C2, which is indicated by the get volumeter G. Thus, if the flux produced by one coil gets linked with another coil due to the change in the flux produced by the coil C1, if there is induced EMF in the second coil, then such an EMF is also called as mutually induced EMF, right? So let us derive what is mutual inductance. Okay, here is, as you can see in this circuit, there is no electrical connections or physical wired connections between C1 and C2. Still you can see there is somewhat of wireless magnetic connection between these two coils, right? And due to that connections only, you are having this current I2 in the circuit number 2, right? So you can say that these two circuits are magnetically coupled, right? C1 and C2 are magnetic coupled. Okay, so this coils or this circuit is said to have mutual inductance. Now mutual inductance can also be defined as property of a circuit due to which the change in current through one coil produces an EMF in other coil placed nearby the induction, right? Now it is usually denoted by M and measured in Henry, right? So now we are going to discuss a little bit important topic, that is magnitude of mutually induced EMF. Okay, so here let us know some terms, right? Here we denoted N1 as number of turns of coil 1, right? So let us write down. N2 will be same, and I1 will be current in a circuit 1, I2 will be coil 2, phi 1 is mutual flux linked with coil 2. And phi 1 is flux produced by coil 1, right? So we all know the induced EMF in the coil 2 due to mutual induction can be written by the Faraday's law of electromagnetic induction, that is E2s minus n d phi 2 by dt, d phi 2 by dt, right? Here the negative sign is due to Lenz's law, because it has to oppose the cause producing it, right? Now here we need to obtain expressions for d phi 2 by dt, right? So in order to get the expression for d phi 2 by dt, we need to write something in relation of phi 2 and I1. That means we need to derive some sort of relation between coil 2 circuit and coil 1 circuit. So let us take a element of phi 2 from coil 2 and I1 from coil 1 circuit, right? Since we need to derive some sort of relationship between them, right? So we can write phi 2 upon I1 into I1. Since phi I1 will cancel out, so there is no differential relation between them, right? Here we can see phi 2 and I1 will be constant, okay, because they both are interlinked to each other. So if you don't disturb I1, automatically your phi 2 will be constant only, right? So the rate of change of phi 2, that is d phi 2 with respect to time, will be equal to phi 2 upon I, that is constant, into di1 by dt. Okay, so what we have done, we have considered phi 2 upon I1 as a constant term, and we have taken differentiation or differential integral of I1, right? So we know that we have now got the d phi 2 by dt expression. So let us term this equation as 1. So, and let us substitute this value d phi 2 by dt into original Lenz's law. So we'll get Et is equal to minus n2 phi 2 upon I1 into di1 by dt. Simplifying further, n2 phi 2 upon I1 into di1 by dt, right? Now here you can see n phi 2 upon I1, n2 phi 2 upon I1 is nothing but your coefficient of mutual inductance. Okay, so here the mutual inductance represents the EMF induced in coil 2 due to current flowing through the C1. Hence we can write it as M21. That is, if you want to simplify in terms of word, you can say that M is nothing but a mutual inductance of coil 2 due to coil 1, right? So what will be M21? It will be nothing but coefficient of mutual inductance, that is N2 phi 2 upon I1. Okay. Similarly, you can also find out mutual inductance of 1, 2. That is mutual inductance in coil 1 due to current flowing in a coil 2. That is nothing but N1 phi 1 upon I2. So it is very simpler. Okay. So here we have derived mutual inductance magnitude and coefficient of mutual inductance. I hope you liked my lecture. If you have any sort of doubt, you can just comment down below. I'll make sure I'll answer them. See you next time.